Hello everyone, I'm Norman Wildberger. Thanks for joining me. We are in the process of largely outlining a new approach to arithmetic, and today, very important and interesting lecture where we try to tackle the problem of how to create negative numbers into our system. So it's quite a long lecture today. There's quite a lot of stuff in it. I'm going to also say a few philosophical or meta-mathematical things beforehand to sort of set the stage. And also there's a tentative aspect or an aspect of this being a proposal, okay? It's not that we have a current, valid, logically correct theory established yet. So we're working towards that. So there will be an element of exploration today as we discover things perhaps for the first time. So we're going to be introducing negative numbers from a notion called an anti-multiset. And the basic idea is contained already in a prior lecture, a couple of lectures in the Math Foundation series, notably Math Foundations 187, The Curious Role of Nothing in Mathematics, and the subsequent videos following that. So that what I'm doing today is largely an extension or modification of what I did there, okay, where I already introduced the notion of an anti-objects and the important role of nothing in this multi-set framework. But we're modifying things by not having the mark as the central fundamental object, but as the empty M-set or zero as the fundamental thing. Okay, but otherwise you'll see that there's a lot of parallel to this. And so if you're interested in this situation, which I hope you are, please go and have another view of this video or have a look at it for the first time if you haven't already done so. Okay, so currently we have a framework which kind of goes on, but it starts with very simple level, just the zero multiset, which is an empty multiset. Then we have natural numbers, which are just M sets of zeros, 1, 2, and 3. And then we have polynumbers, which are M sets of natural numbers. That one there, called alpha 0. There's another one. Here's an M set of natural numbers, which we can interpret it as the polynomial 2 plus alpha 0 plus alpha 0 cubed. And then multi-sets of polynumbers, like this thing here. This is an M set of polynumbers, because that's a polynumber, that is, and it has the interpretation of a polynomial in more than one variable, so alpha 0 squared corresponding to that, plus 2 alpha 1 alpha 2 corresponding to these two elements, plus alpha 4 corresponding to this one. And we can go further. We have an obvious sort of inductive or sequential process in extending not just objects, but also operations to further levels down. And we also have a nice way of visualizing this kind of thing in an alternative way using trees in the language of computer science. But notably, the objects that are appearing here, there's numbers appearing, but they're all natural numbers. So we today want to move to try to extend our number system to include negative numbers. That's a very interesting challenge. Okay, so broadly our aim is going to be to introduce a new number, -1, which I'm also going to write as 1 bar. So actually for a lot of purposes I prefer this bar notation for negative numbers, and I'm going to largely be following that, and I urge you to also consider using that. Okay, so it's very useful because then this minus sign is not confused with the subtraction operation. Okay, and it also minimizes the necessary use of brackets in a lot of situations. So in either case, I'm going to use 1 bar typically. What we want to establish about this number is that ordinary 1 plus 1 bar equals 0. And also that 1 bar times 1 bar equals 1. So those are two crucial properties of this new number that we're trying to introduce. And then after we have 1 bar, then we're going to introduce more general negative numbers so that we get a kind of a integer number line with the natural numbers extending to the right like this, and negative numbers 1 bar, 2 bar, 3 bar, etc. And we want the usual laws of arithmetic that are familiar to us in the natural number domain to extend to this larger domain of integers. Then what we want to do, or as part of this process, is we want to extend these numbers to poly and multi and beyond. so that polynumbers and multinumbers and further things may also use these negative numbers as constituents to build up these more complicated structures. And so we end up with an extension of the usual laws of algebra to incorporate negative numbers. And hopefully we'll get some new insights in this way. So let me say a few words about negative numbers. It's important to realize before we start, okay, that negative numbers have been a source of insecurity, of questioning, of skepticism for a long time. Most ancient civilizations, even if they were reasonably proficient with arithmetic and algebra, for example, even going back to the Babylonians, but also the Greeks and the Arabs and Chinese and so on, most of these civilizations had ways of avoiding the explicit usage of negative numbers. So, for example, if we wanted to solve the equation x squared plus x minus 1 equals 0, that quadratic equation, they would have preferred to rewrite it as x squared plus x equals 1. So there's only natural numbers appearing. This unsureness about what negative numbers are and what their role is extends even into the modern era. Descartes, René Descartes famously, the father of modern geometry and a key figure in 17th century mathematics, was dubious about the role of negative numbers and explicitly tried to avoid them in his geometry. So the usual Cartesian coordinate axes that we teach undergraduates as being a result of Descartes' thinking, actually, with its usage of a number line with both positive and negative values, is a little bit foreign to Descartes' thinking. He preferred to think in terms of having two axes labeled by positive numbers, okay? So he restricted himself to what we might call the sort of upper quadrant. And so we have to have some respect for the difficulty in establishing a sound theory of integers. And you might like to think personally, okay, just yourself, how you go about establishing a proper theory of integers. I know you've all learnt about integers somewhere in primary school, and you've sort of been taught these rules, and perhaps you can remember back in grade 5 or whatever, when you were told that minus 2 times minus 3 is plus 6. And maybe you're asking, well, if minus 2 represents a debt, like instead of having 2 apples, I have minus 2 apples, means that I owe somebody else 2 apples. What does it mean to multiply minus 2 with minus 3 and get plus 6? And how do we really establish the laws of arithmetic in this integer domain? Have you actually gone through that yourself, even if you're a professional mathematician? Chances are you probably haven't actually. Okay? So this is something that we sort of assume as sort of background. Yeah, we all have the faith in this, but do we actually have a coherent theory? So that's a starting point here. Okay, we have to recognize that there's something potentially problematic or difficult or challenging about negative numbers. And today I'm going to be challenging you further by introducing them to you in a very novel way. Okay, that surprisingly really ultimately relies on 20th century physics for its intellectual support. So let's begin our exploration and try to deduce what likely we have to have if we want to have a consistent theory of negative numbers, extending this multiset arithmetic that we already have. Okay, so the primary thing that we're aiming for is, first of all, a minus 1 or a 1 bar. So let me remind you that in our system, the number 1 is the M set consisting of 0. And 0, of course, is the empty M set. So this new thing that we're interested in, this minus 1 or 1 bar, it's going to also be an M set because all of the things in our world so far are M sets. So we can posit that this is a new M set with something in it, but we don't know what that thing is that's inside here. Okay, so let's put it represented with a question mark. Okay, so what do we need to have happen? We want that 1 plus 1 bar is 0. So 1, that's M set 0. 1 bar is this M set with a question mark in it. Okay, and we have to add these two things. How do you add M sets? Well, you dump them both out into another M set. So we're creating a new M set, and the 0 goes in that M set, and this question mark, whatever it is, also goes in there. And what we want to have happen here is that the result of that is 0, which is the empty M set. So this question mark has to have the property that if you put it in a box with 0, the result is an empty box. That's necessarily what's required in our framework. There's no getting around it. So this is a very unfamiliar situation to, mathematics in the last 10,000 years. Right? There's nothing in mathematics that's really like this, that gives us any kind of prior intuition about such a thing. We don't have situations where we have one thing being completely canceled with something else to create nothing. Not 0, but nothing. Okay? This 0 and this question mark are creating nothing. But 20th century physics, completely remarkably, has discovered such a phenomena. And crucially, it's one of the most important developments, in fact, of 20th century physics. That was the discovery, essentially by Paul Dirac, of antiparticles, starting with the antiparticle for the electron, which is called the positron, which is a particle which is very similar to the electron in most aspects, has the same mass, same spin, that kind of thing. But crucially, it has opposite charge. And moreover, has this property that if an electron and a positron get close together, then boom, they mutually annihilate each other in a flash of light with some photons being emitted. So they have rest energy. That energy has to go somewhere, and the energy is carried off by two photons going in opposite directions so that linear momentum is conserved. So this is a totally remarkable thing, and especially when it became clear that this is not just a phenomena involving electrons and positrons. The positron was found a few years after Dirac postulated its existence. But moreover, and sort of spectacularly, it's now the case that it appears that almost every particle that is known, all these elementary particles, have corresponding antiparticles, which essentially have the same kind of relation, that they more or less share most of the properties with the original particles, except that when you bring two of them together, the particle and the antiparticle, boom, they annihilate each other releasing some kind of energy. Now, this is a remarkable thing. I'm going to have to say more about that. But that's really our motivating idea, that this is exactly what we're needing here, minus the energy transmission. Okay? 0 combined with something or other gives us nothing. So what we're going to do is we're going to introduce such a new object into our mathematics. Okay, we have to create an antiparticle for our fundamental object, which is 0, the empty M set. And I'm going to give it the name 0 with an A above it. A, of course, standing for antiparticle. We're going to call it anti-0. So the anti-0 is this expression. It's a new symbol, okay, with the property that if you have an M set containing 0 and 0A, then they mutually cancel each other out, and we just get an empty M set. So the question, well, what actually is this thing? We're not going to answer that question anymore to say, well, it is only a symbol. We're dealing with a language of symbols, okay? And just like this is a sort of a symbol, this is a new symbol that we're introducing in order that we're able to ultimately come up with a -1. And it's pretty well necessary if we're going to do arithmetic in this multi-set kind of framework. So curiously, if this arithmetic had been discovered centuries earlier, then probably the physicists would have been much more inclined to have discovered the antiparticle kind of symmetry that exists in nature, which is such a profound and remarkable symmetry, perhaps earlier. Along the lines of the physicists, I do have to remark one more additional thing, however, that this symmetry that we have is a broken symmetry, in that the actual world that we live in is predominantly made out of matter particles and not antimatter. So antimatter is something that we only can cook up under rather extreme circumstances, or perhaps in cosmic rays or something. But it's not typical, okay, at least as far as we can see. Everywhere we look, we see matter, not a lot of antimatter. And so this imbalance between the matter and the antimatter is a huge problem for physicists and for cosmologists. It's one of the central problems in 21st century physics, is to explain this apparent asymmetry between these two kinds of things, which otherwise seem to be quite parallel. So now I want to explore with you some consequences of this fundamental idea of having this somewhat symmetrical object, anti-zero, added to our arithmetic. So we're going to develop some consequences. But I want to emphasize that this is in an exploratory fashion. That is, we do not know actually if this proposed arithmetic that I'm laying out here for you actually is a consistent arithmetic. Okay, we do not know that. We would like that to be true, okay, and maybe there's some indications that it might be, but this is still a very important question, and we can't get around it. And in particular, what we are definitely not allowed to do is what the modern analysts do with respect to real numbers, which is basically to say, well, we don't actually have a proper foundation for real numbers, so let's just stomp our feet and sort of axiomatically suppose that we have a set of real numbers that obeys the following pleasant properties that we would like to have happen. Okay? We are not allowed to do that. We have to establish everything correctly in a bona fide way, right? So there's a lot of work to be done here in, first of all, checking whether or not what I'm proposing actually makes sense, and maybe it doesn't. Okay, maybe one of you will next week discover some contradiction. Okay, it's possible. I'll wear that. Okay, that'll be fun. Then we can revamp things or look in an alternate direction, or how we have to modify things. Okay? But we're not just going to assume that what we want to be true is going to be true just because we want it to be. Sorry, analysts, but we want to do things correctly here. All right, so let's proceed with some possible implications of the existence of this anti-zero. Let's look at this equation, 1 times 0 equals 0, which is a valid equation in our system so far. We want that still to be valid. So there's a basic idea that all of the prior arithmetical rules that we currently have for the objects that we currently have, we want them still to be valid, even when we're extending the arithmetic to include these new kinds of objects. Okay, what is this? Here is 1. It's the empty set contained in the set. And 0, of course, is the empty set. And now, crucially, this empty M set can be replaced with the M set consisting of 0 and anti-zero. So like what the physicists call particle-antiparticle creation. Okay, this is an important idea that to the physicist, nothing, like a vacuum, is not exactly completely empty, because bubbling out of the vacuum, you can create these particle-antiparticle pairs, just like we're doing here. This is very parallel to roughly the kinds of things that they're doing. Okay, so this has to still be a reasonable rule. So what happens when we apply the usual laws for multiplying this thing by this? Well, the usual law is that we should take the M set consisting of sums of elements here and elements here. So that would be 0 plus 0 and 0 plus anti-zero. Well, 0 plus 0 is 0. And 0 plus anti-zero, we don't know what that is yet. But we do know that the result of this thing had better be the right-hand side, which is the empty set. So this object, 0 plus 0a, or 0 plus anti-zero, better be anti-zero, because we wanted to cancel with this 0 to get nothing. So we get a rule. we get the rule that 0 plus anti-0 is anti-0. And if we did it the other way around, symmetrically, anti-0 plus 0 is anti-0. So there we have a first rule of arithmetic combining this new object anti-0 with a prior object 0. And let me remind you that this is sort of consistent with the way we think 0 works, that when we take 0 and we add it to something, we get that other something. Okay, and here's another rule that we want to have satisfied. 0 times 0 is 0. Empty M set times empty M set should equal empty M set. But this empty M set can be thought of as the M set 0 anti-0. Similarly, this one is 0 anti-0. And when we think about it this way, to multiply those two, we have to form all possible pairs and add them. So we have to have 0 plus 0 as one entry, 0 plus anti-0 as another entry, anti-0 plus 0 as another entry, and anti-0 plus anti-0 as another entry. Now, 0 plus 0 is 0. 0 plus anti-0, we've just established that's anti-0. And this one here is also anti-0. But anti-0 plus anti-0, we don't know yet what that is. Nevertheless, we can do some cancellations because this 0 and this anti-0 are together in this M set, so they are going to mutually annihilate each other. So they're gone. What we have left is a single anti-0 there, and this combination anti-0 plus anti-0. And hopefully we're going to get the right-hand side, which is the empty M set. So again, we must have some mutual cancellation. We have an anti-0 here. So this thing here had better be 0 because that's the thing that annihilates with anti-0 to get nothing. So we can conclude that anti-0 plus anti-0 equals 0. Okay, so for our next derivation, let's do something similar to what we just did, but a little bit more generally. Let's consider an M set consisting of some object M. Okay, where M is some M set or object in this arithmetic. And we're again multiplying it by 0. Typically, we want that to be 0. Okay, that's what we sort of expect. So in terms of M sets, there's M set M. 0 is, of course, just the empty M set. And that, again, can be replaced with the M set consisting of 0 and anti-0. So when we now do this multiplication, we get something similar as before, but a little bit more generally. We get M plus 0 as one of the entries, and M plus anti-0 as the other entry. M plus 0 is M, and here we have M plus anti-0. And the right-hand side ought to be the empty set. So we see that for any M set or object M in this arithmetic, if this is going to be valid, then there has to be an object which cancels M in the same way that anti-0 cancels 0. So this is a huge extension. We are necessarily forced to recognize that this particle-antiparticle symmetry extends far beyond the 0-anti-0 pairing. Just like Dirac's electron-positron kind of symmetry actually ended up extending much further to, in fact, general particles. In fact, these days it's recognized that that's valid even for, at the atomic level, and in principle even at the molecular level, and even at the level of human beings. It's possible that there could be an anti-Norman, exactly more or less the same as me, but made entirely of antiparticles. Okay, so the same kind of thing is happening here. We have this big enlargement of this symmetry, okay, we have this divide between matter and antimatter in the physical level, between M sets and these anti-M sets in this arithmetical framework. Okay, so what should we call this thing? Well, obviously we should call it M with a superscript A, okay? We'll call it anti-M. Okay, so we want this anti-M to have the property that if you have M and anti-M in an M set, like they're just objects in an M set, that they find each other and they cancel, poof, they're gone, and we just get nothing inside the this empty M set. And what we've established up here, okay, is that that this particular combination, that capital M plus anti-zero, is going to be this anti-M. In other words, this anti-M is actually M plus anti-zero. And we could do it the other way around, anti-zero plus M. And in particular, if you have M being anti-zero, we play this same game with anti-zero, which is an object in our world, then the anti of the anti-zero should be a zero. Because if we replace M here with anti-zero, then over here we have anti-zero plus anti-zero, which we've just established is zero. Okay? So that establishes that if we take the anti of zero and then we take the anti of that in that sense that I've just described, then we're going to get back zero. And now I'm going to play a very similar game as to the previous ones, except that I'm going to move up or down in the operation ladder. So instead of thinking about multiplication, I'm going to think about the caret operation. So let's look at the equation 1 caret 0 equals 0, which is a valid equation in our system. So if it's a valid equation, then it should still be valid after we replace the empty set here on the left-hand side with the set 0, anti-zero. So when we do this caret operation, let me remind you that what we're doing is we take all possible pairs and we have to multiply them. So we have to take 0 times 0 and 0 times anti-zero. The 0 times 0 is 0. So this thing here, again, since we want this to be 0, okay, maybe I should write that. We want this to be 0. So it follows that this combination, 0 times anti-zero, had better be anti-zero. And other way around, anti-zero times 0 equals anti-zero. And I've put triple exclamation mark here. Okay, so please make note of this. This is an unfamiliar aspect of this arithmetic. Okay, so perhaps some of you are getting a little bit nervous, and this is a cause for pause here. Okay, because we are declaring that we have some object, so that when we multiply it by 0, we do not get 0 anymore. You know, usually that's always what happens when you multiply by 0. You multiply by 0, you're going to get 0. But here in this world, it appears that 0 times anti-zero is not 0. It's rather anti-zero. Okay, so then we can do the same kind of thing, replacing the 1 with 0. 0 caret 0 equals 0. That gives us this equation. Do the multiplications. 0 times 0, 0 times 0, a 0 times 0, a 0, or 0 to the a, 0 to the a. And this is 0. 0 times anti-zero. We've just established that's anti-zero. This one's also anti-zero. We've just established that. These two here. So this unknown one here can be determined because now again we have these cancel. Okay, we just get anti-zero and this anti-zero times anti-zero. And since we want that to be the empty M set, we must have that this combination is actually the thing that cancels anti-zero, which is 0. So we get anti-zero times anti-zero equals 0. So we have two things multiplying together, basically squaring, getting 0, but the actual object itself is not 0. It's another sort of unpredictable kind of thing. It's counter to our usual intuition. Great, so now we can write down addition and multiplication tables for 0. The 0 level of our arithmetic, which now contains not just 0, but also anti-zero. So at that 0th level, there are now two objects. So there's an addition table. 0 plus 0 is 0. 0 plus anti-zero is anti-zero. Anti-zero plus 0 is anti-zero. And anti-zero plus anti-zero is 0. And there's a multiplication table, which is 0 times 0 is 0. 0 times anti-zero is anti-zero. Anti-zero times 0 is anti-zero. And anti-zero times anti-zero is 0. Notably, that these tables are pretty well the same, except for the operation sign there. They're exactly the same. So at the level of 0, the operations of addition and multiplication cannot be distinguished. Okay, they cannot be distinguished. So here's another exercise if you like this kind of thing. Show that for any m set or object m which is not equal to anti-zero, we have m times anti-zero, same as anti-zero times m, is anti-zero. And this is quite interesting because of this requirement here that we have to restrict ourselves. It's not true, this is not true if m is equal to anti-zero itself, because if m is equal to anti-zero, anti-zero times anti-zero, that's equal to 0, not anti-zero. Okay, so that's already suggesting that's quite an interesting sort of thing, that we have to be mindful of this sort of exemption to this general rule. Okay, there's something interesting happening here, and it makes us be motivated to really investigate further the internal consistency of this arithmetic. Is this arithmetic really consistent or not? Okay, so having spent quite a lot of time on these anti-zeros and their various properties, now let's move to negative numbers. Okay, that's a different kettle of fish because we are still using the anti property, but we're sort of putting it one level down in an m set. So specifically what we're going to do now is introduce -1, or preferably 1 bar, define that to be the m set consisting of anti-zero. Let me remind you that 1 is the m set consisting of 0. So now -1 is the m set consisting of anti-zero. And if we add the two of them, well then obviously we get an m set consisting of an anti-zero and a 0. They annihilate, we just get the empty set. So yes indeed, 1 bar plus 1, or 1 plus 1 bar and the other way around, is indeed 0. So this fundamental property that we require for -1 or 1 bar is satisfied. Let's look at 1 bar times 1. There's 1 bar, there's 1. We're multiplying, so we have to take all possible sums of elements. So we have an m set with anti-zero plus 0. We know that that sum is anti-zero, and so we see that -1 times 1 is -1, and similarly 1 times -1 is 1. And in the same spirit, -1 times -1, there's -1, there's -1. We multiply them, we get anti-zero plus anti-zero inside. We know that particular combination is 0. Okay, we've already established that. So we get that 1 bar times 1 bar equals 1. Okay, now that we have -1 or 1 bar, we can introduce integers, or negative numbers first. So definition, if n is a natural number, then n bar, otherwise known as -n, is going to be defined by 1 bar times n. So for example, 2 bar. By definition, that's 1 bar times 2. There's 1 bar, the m set consisting of anti-zero. Here's 2, the m set consisting of 0, 0. We multiply them, so we have to form anti-zero plus 0, anti-zero plus 0. Each of those is anti-zero, so we get anti-zero, anti-zero. So that's what 2 bar is as an m set. It's the m set consisting of 2 anti-zeros, in parallel way to the fact that 2 is the m set consisting of 2 zeros. So let's do some arithmetic with integers. Say 2 plus 3 bar. So there's 2. There's 3 bar, or -3. Adding the m sets, we just dump them all together. So we get a 0, anti-zero, anti-zero, anti-zero. We get some cancellation because they're in the same m set, so they can interact with each other. Okay, this 0, that anti-zero, perhaps they annihilate. This 0, that anti-zero, perhaps they annihilate. We end up with a single anti-zero in the m set, so that's 1 bar, or -1. 2 times 3 bar. Well, there's 2 times 3 bar. We're taking the product, so we have to form all possible pairs and form their sums. So 0 plus anti-zero, well that's anti-zero. All of these are anti-zero. Anti-zero, 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 anti-zero. We get 6 anti-zeros, which is 6 bar, or -6. So you can kind of see that the usual arithmetical laws for integers are going to be satisfied here. In particular, y minus 2 times minus 3 is 6 is going to be self-evident, simply because anti-0 plus anti-0 is 0. Okay, in our final slide, I want to show you that this notion of negation actually now extends much further. So usually in algebra, when we introduce negative things, we have to sort of do it separately at various levels. When we introduce polynomials, we have to define how we're going to define negative multiplications, etc., etc. Here, essentially the same point of view that we already have allows us to extend this negativity all the way down. And again, we have to draw heavily upon this prior understanding of anti-M sets. Okay? So suppose M is an arbitrary pure M set. So it's an M set just consisting of things that we already are working with, no other kinds of mathematical objects. So we're going to define M bar, or minus M if you like, just to be 1 bar times M. And now we can deduce that if M is a pure M set, then what this really is doing, okay, it's taking the anti of each of the elements of M. So M is a box, okay, which has a lot of little boxes inside. These are the elements. Those boxes themselves may very well have all kinds of stuff inside each one of them. That's fine. But the negative of the entire big box is, according to this, what you get when you consider the box consisting of the antis of each of the elements. The anti of this little element, the anti of this little element, the anti of this little element, and so on. Okay, that's what the negative of the entire M set is. So why is that? Well, M bar, according to the definition, is 1 bar times M. 1 bar, there it is there. The M set consisting of anti-0. M is the M set consisting of, let's say, little m's, where M is in M. So we have a whole bunch of these elements of M. How do we multiply things? Well, we have to take all possible pairs between these guys, and we have to add them. Well, there's only one of them here, so we're just taking all pairs of the form OA and M, and we're adding them, so we're getting OA plus M as we run little m through capital M. But OA plus M, if M is any M set, is the anti of M. Remember, that was one of the rules that we established, that you add anti-0 to anything, you're getting the anti of that thing. So each of the elements of M is being antied by the effect of multiplying by minus 1. That's another way of thinking what negation is in this world. Okay, it's unfamiliar. It's something that we need to get our heads around. In my next video, I'm going to try to give you some more illustrations of how this works. There's much more to be said here, and this has all kinds of very interesting consequences. And still exploration to be made in terms of whether this actually, rings true and is a consistent theory, which we do not yet know. All right? So this is a prospective arithmetic. There's much to investigate and to think about here. I'm Norman Wildberger. Thanks for listening.